So now we're going to switch a little bit here and talk about soil structure. And soil structure is how the particles are grouped together into stable collections. And it's generally what's gluing them together is organic matter. And it's also when they are forming these groups, they're called PEDs or soil aggregates. Cycles of wetting and drying and freezing and thawing can kind of promote these PED developments. A well-developed soil structure enhances the water and the air movement and root growth in a soil. So soil structure is classified by the shape and size of the PEDs. For our garden soils, we kind of want this granular structure. And it's little small balls of soil. They easily separate. Plant roots can go through them. And again, parent material is going to play an important role in this. There are blocky structures and there are prisms and columns and all sorts of different soil structures that can form. But this is kind of where we want to get to here is this nice soil structure. And soil structure is really important because these little aggregates or PEDs are important because they influence porosity and permeability. So here we have a sand grain and there's silt and clay and organic material here. And the pores within these little individual PEDs, they're really small, but the pores between those PEDs are fairly large. So good soil structure reduces that potential for crusting. If we didn't have these large pore spaces, it would be really hard for water to infiltrate into the soil. And that is what happens in a clay-rich soil. We get that soil crusting. So if you apply water to this, it's going to have a hard time infiltrating. And crusting is, like I said, more common in clay-rich soils. It'll form in the middle of a lot of our valleys because that's the low point and that's where the fine material finally settles out in our valleys. But we do other things all on our own to degrade soil structure. And the three most common are compaction, erosion, overworking, or overtilling the soil. So let's go back to that composition of an ideal soil. Remember, we said we had the 50% of the mineral fraction and 50% air spaces. 25 of the air spaces were 25% is filled with water and 25% is filled with air. So half of the soil is pore spaces and half of that is air and half of that is water. When we compact the soil, and soil is more easily compacted when it's wet, what we lose is the airspace. The water's still there, it's still there in the soil in between the PEDs, but what we lose is the airspace. And sometimes that's kind of hard to visualize, so I kind of like this diagram. So here we have a non-compacted soil. Again, the gray are the soil particles, the blue is the water that surrounds them, and the white is the air that's in between all these different PEDs. And when we compact the soil, we are losing that airspace. It becomes harder for water to move through the soil, for animals to live in the soil, for plant roots to grow in the soil. This is a kind of a cool diagram showing the problems with compaction. These are two corn plants, and this one here on the left was grown in a very compacted soil, and the one on the right was grown in a non-compacted soil. And you can see that the root development is significantly better here in the non-compacted soil. Well, as we all know, being gardeners, if you don't have good roots, you don't have good shoots. So I would venture to say that the corn ear production on this left-hand plant in that compacted soil was very poor indeed, whereas ear production was probably much, much better in this plant. The wetter the soil, the worse the compaction effect can be by mechanized equipment, even by repeated walking on a very wet soil. So this is a cool little study they did in the University of Minnesota, and they put pressure detectors in the soil And then they drove heavy equipment over the soil, dry soil, moist soil, and wet soil. And they looked at how many pounds per square inch and how far down in the soil depth it went. And you can see that there was 3 PSI of pressure 24 inches down in that really wet soil. So the wetter the soil is, the worse the compaction can be. And this picture always kind of makes me cringe because they've driven heavy equipment over here and this soil is sopping wet and they have just compacted this soil. It's gonna just take forever to get this soil back. So try to avoid walking or driving on very wet soil and try to avoid working wet soil. The next way that we kind of degrade soil structure is through erosion. We've talked about how long it takes soil to form. So you really don't want to lose it. You want to keep a cover on the soil, plants or mulch or something. If you, especially if you're dealing with a slope, you want to provide drainage paths and you want to armor them to reduce the potential for erosion. The water can form surface runoff and it'll move down slope. And when it does that, it's going to take the soil with it. Another thing I think that I need to mention, especially because we have been having long, dry, hot spells here, is after a long period of drought, our soils will have a hard time absorbing water. The water will actually run off the soil surface rather than infiltrating. So it is called hydrophobic soils. And remember we talked about water's kind of attracted to itself because it has that partial charges at either end. Well, Bill Nye, the science guy, did this great experiment that demonstrates this nicely. And I think you can find it on YouTube. But as an experiment, Bill takes 2 pie pans and he fills them with water. And then he takes 2 sponges and one is damp. It's had all the water squeezed out of it, but it's still a little bit damp. And one is completely bone dry. And at the same time, he drops them into each of them into a pie pan filled with water. And contrary to what you might think, that damp sponge actually absorbs more water and does so quicker than the dry sponge did. This is very similar to what happens to our soils if they're not irrigated, if we haven't had rainfall in a long time. The soils are so dry they can't absorb the water. And they especially can't absorb it as quick as it's applied, especially if it's a thunderstorm event. If the soils are in any kind of slope and if the ground is bare, the stormwater is just going to flow over the soil surface, moving some of the soil in the stormwater runoff and depositing it somewhere else. So we want to make sure we protect our slopes because of this increase in the potential for erosion on a slope. You can use plants, you can use mulch, you can use drainage pathways and other steps. This is a beautiful example. These people, bought this house with the backyard that has a slope on it. They've got this nice lawn area. And if they didn't do something up here, every time there was a storm, this would gradually wash down onto their lawn. So what they've done is they've planted some plants and ground cover. They've put mulch here. They've got a staircase here, and off the staircase, it's hard to see. They've got little places where if there's flowing water, it can move off into the vegetated areas. And then they have plants here that are buffering that lawn area. So anything that runs off is going to hit those plants first, or it's going to hit this little rockery, and the water is going to infiltrate there and not move debris and soil and everything else onto their lawn. So they've done a really, really good job to minimize their potential for erosion. Storm events can create that potential for erosion. So one thing you can do is try to redirect the rain and slow the flow. This is a really simple way to do it. Here's the downspout of your gutter. And rather than having it chew a hole in the lawn right here and wick up on your foundation, You put this plastic tray, I've also seen them made out of cement. It slows the water, it disperses the water, and it makes the water flow outward onto the lawn. This is a common way that they deal with rain, especially in the Pacific Northwest. They install a rain garden. They choose plants that don't mind their feet being wet for a certain period of time, and they redirect the gutters there. And so then the rainwater has a chance to infiltrate here and water these plants. It's less likely to be used in our area because you have to provide supplemental irrigation for these for the plants that are in the swale. And in areas of lots of water, though, this is a common thing that they do. And this I just thought was a very cool picture. It's from Portland, Oregon. And they've created the garden area to direct the building runoff. And it's just created this nice little feature. And it's beautiful whether there's rain pouring out or not. And the last way that you need to reduce the potential for erosion is to check your irrigation off often. And I'm as guilty of this as everybody else. You know, I troubleshoot it in the spring and I go to work during the day and I'm not aware that something's happening. And especially if you're on a slope or something like that, that irrigation, a leak in your irrigation can cause some erosion features to form. And the last way that we can degrade our soils, well, the last common way, is by overworking it. You can cause compaction, you can reduce the soil structure if you work a soil that's too wet or too dry. So you can kill the soil biota also. Now the tillage hard pan, plow pan, that's if you're doing a rototiller. The rototiller only works like 4 to 8 inches depending on the size of tiller you have. And when you work it over the same area over and over again, you're only working that top 4 inches that the rototiller reaches, but you're actually compacting the soil that's beneath that. So how do you know if your soil is too wet or too dry? That's a hard one. You can tell the two extremes, right? If you squeeze a handful of soil and water squeezes out of it, then it's too wet. And if you've put your rototiller down and started rototilling and there's a rooster tail of dust behind you, then it's too dry. Where's that sweet spot? What I generally find works for me is I grab a handful of soil, and that's my hand in the picture there, and form it into a ball. And then I take the finger of my opposite hand, the index finger, and just give the ball a poke. And if that breaks up that ball of soil, that's about the right moisture level to start working your soil. So there's one more physical kind of characteristic of soils that I want to talk about, and that is to avoid creating a soil interface. When water is moving through a soil and it reaches a horizontal or a vertical interface between different soil types, it won't move into the new different soil type until it's saturated the first soil type. And this is a series of pictures showing it. This top layer that's a little bit lighter colored here is a silty loam, and below it is a sand soil. And they're applying water very slowly. And the water is actually moving laterally rather than going into that sandy soil. And it will continue to do so until this top layer is saturated, and then it moves into the lower layer. So I just want you to be aware of this. This is how water is going to behave if you have an interface or you create an interface. But you can use this knowledge to your advantage. And here's another experiment that they've done. And here's the soil, and below it is sand and gravel. And it actually will completely wet that soil layer before it moves into the sand and gravel. And it seems counterintuitive. It seems that gravity would be helping out here, but it won't move till it's saturated that different layer. It won't move to the lower layer. So we just want you to be aware that that can happen. So don't put a rock layer, a big layer of rocks in the bottom of your planting pot or in the bottom of your raised beds. You're creating an interface there. And so just put one to cover the drainage hole to prevent soil from spilling out of the pot. And if you have raised beds, you're going to want to work the soil that you place the raised bed onto. So put like 4 to 6 inches of the soil you're bringing in to your raised bed, and then work it with the native soil underneath, and then put the next layer of soil and work it, so that you're not creating an interface. You're not creating two distinctly different kinds of soils. But wait, and this will make more sense later. What if you have a salty native soil or a really clay-rich native soil? You could intentionally create a soil interface. When you place the raised bed on top of those problem soils, it requires a lot of attention to watering times and monitoring that the raised beds don't become saturated and that there's no air spaces, so you eliminate all the air spaces in the soil. But you could use that to your advantage in those particular situations. So we've talked about adding organic matter all through this, and it is just about as close as you can get to a panacea, a solution or a remedy for all the difficulties we encounter with our soils. So it does improve water infiltration in the clay soils. It increases water and nutrient holding capacity in sandy soils. It helps form the soil in the stable aggregates, acting as that glue. It reduces soil compaction. You can put organic material on top of a compacted soil, leave it in place, and it will gradually loosen things up. But the other thing it does is it feeds the soil biota. And we forget that soil has a living component. So there's lots of living creatures in the soil. We talked about there's also dead decomposing things in the soil. There's this huge food web, and all these little things work together, even on a microscopic level. And if we don't have this living component of the soil loses its ability to support plants and to recycle nutrients. So soil organisms are the key to that soil food web and maintaining that soil ecosystem. And here's a nice picture of a worm. So we have the living organic material, the decomposing organic material, the living plants, and some dead root parts. So this picture kind of shows you everything of things that you can see with the visible eye. So these little earthworms, they recycle nutrients. They burrow tunnels in the soil. They process the soil through their digestive tracts. They leave behind nutrient-rich worm castings, which is worm poop. They not only release nutrients to the soil, but they also aerate the soil with their burrows. Microorganisms such as bacteria and fungi, things we can't see, they decompose that organic matter and cycle the nutrients into the soil too. So we want to be careful about not overworking the soil to kill the biologic component, and not using too much fertilizer and cooking the living organisms in the soil. I like this diagram, but people always give me a hard time because we do not have one vertebrate for every square meter of soil in the desert. So granted that we live in the desert, the takeaway from this graphic is that for every animal you can see, this vertebrate, there are millions, sometimes billions of creatures you can't see in the soil. 1 cubic yard of soil can contain as many as 1 billion colonies of bacteria, 100 million fungi, 100,000 algae, billions of protozoa, thousands of mites, nematodes, insects, and earthworms. And all these creatures have this intricate little dance going on with the physical and chemical properties of the soil. So here we have some nematodes and microscopic bacterial colonies. Here is sand grain, and here is the silt, clay, and organic material kind of complexes that surround the sand grains. And here's a root hair, and the root hair is exchanging with the nutrients that are held in the clay and organic matter complex here. And this bacteria is converting things in the soil, converting elements in the soil, into forms that plants can uptake. So there's just this beautiful, intricate little dance that's going on in the soil.